Hello, welcome to a video about linear and volume expansion. For some reason, the school iPad thinks it's a bit too good for my picture of a Nintendo 64 expansion pack, but it should be printed on your handout. I strongly recommend playing a Nintendo 64 if you can get your hands on it. I would play Mario Kart or Pokemon Stadium. Most solids, liquids, and gases expand when heated, and in stage 1 physics, you'll need to be able to describe applications of the expansion of matter due to heat transfer. So, most materials expand when heated and contract when cooled, although there is a very prevalent example on Earth which doesn't contract when cooled. See if you can think about what it is. You might have covered it in bio, I'm not 100% sure. And the amount that materials, so generally the amount that materials expand or contract depends on the material itself and its state of matter. We're going to look at linear expansion first. So this is an expansion in length. So particles in solids with a temperature greater than absolute zero, so greater than 0 Kelvin, vibrate about a fixed position. Vibrational kinetic energy increases when the temperature increases. So therefore, if the temperature increases, the particles will separate a little bit because of that increased vibration. As a result, the average distance between each particle increases, and when you zoom out back to the macro level, this causes linear expansion of the overall solid. This only occurs with solids, and this is because liquids and gases don't have a fixed shape. So because their particles aren't held in a position, they won't expand, or the overall volume won't expand lengthwise. Change in length of a solid is proportional to the change in temperature, and this is given by the rule outlined here. So change in length is equal to the coefficient, which is this thing here, coefficient of linear expansion multiplied by the original length and multiplied by the change in temperature. The coefficient of linear expansion is a measure of fractional change in length per degree change in temperature. So its units are per Celsius, or Celsius to the -1. Units of length is obviously in meters, and temperature or change in temperature is measured in degrees Celsius. So if you need to measure the change in temperature, this will be equal to the final temperature minus the original temperature. So as an example, we've got Sydney Harbour Bridge. It's a steel bridge. At 4 degrees Celsius, its length is 1149 metres. We need to calculate its change in length on a 40-degree day if the coefficient of linear expansion of steel is 12 by 10 to the -6 per Celsius. So to do this, we'll just write out our rule, which is change in length is equal to coefficient of linear expansion multiplied by the original length multiplied by the change in temperature. Our coefficient of linear expansion, really done a terrible job of drawing it, but whatever, is equal to 12 by 10 to the -6 per Celsius. And then the OG length, original length, is 1149 metres. Our temperature, change in temperature, is going to be equal to final temp minus the original temp. So that will be 40 degrees minus 4. So plug all of that into our rule. We'll get 12 by 10 to the -6 multiplied by 1149 multiplied by the change in temp, which is 40 minus 4, which is 36. If you pop that into your calculator, you'll end up with an expansion of about 0.5 meters, so half a meter. So this is obviously a significant amount. So Sydney Harbour Bridge is fitted with hinges to allow for its expansion and contraction depending on the temperature, and this prevents its collapse. Generally, modern bridges, train tracks, concrete highways, walls, they're all fitted with expansion joints, and this allows for this expansion during heat and contraction during cooler weather or temperature. So moving on to volume expansion, this is an increase in the volume of a material, as you might imagine. It can apply for solids, liquids and gases, and it's due to a change in temperature. The rule is this bad boy here. Change in volume is equal to the coefficient of volume expansion multiplied by the original volume and then multiplied by the change in temperature. The units don't necessarily have to be meters cubed. You could use milliliters or liters, just as long as you're consistent with the change in volume and the original volume. And this is because your coefficient of linear expansion, its units are per Celsius, and your temperature units are Celsius. So when you're multiplying these together, they'll cancel out and you'll just be left with whatever units you're using here. So as long as the volume ones are consistent, you can use whatever volume units you please. So as an example, you've got liquid nitrogen, which is negative 196 degrees Celsius, and it's poured onto a balloon that's filled with 500 ml of air, and the air is at 20 degrees. Given the coefficient of volume of expansion of air is 3.4 by 10 to the negative 3 per Celsius, calculate the change in volume of the air in the balloon. So similar with the linear expansion, you just write your rule. Make sure you're using the coefficient of volume expansion and then change in temperature. So our coefficient of volume expansion is going to be 3.4 by 10 to the negative 3 per degrees. And then our original volume is 500 ml. Our change in temp, so final temp minus original temp, is going to be negative 196 degrees minus 20 degrees. From there, sub everything in, so we'll have 3.4 by 10 to the negative 3 multiplied by the original volume, which is 500, multiplied by the change in temperature. Negative 196 minus 20 is going to be negative 216. You multiply all of this together and you'll end up with about 367 mils. And that is how much the volume decreases in the balloon. So because there's a negative there, it means that the volume has changed in the negative direction, so it's decreased.